meeting of all together, and today we're going to start with Professor Carabali from Universidade Civil. He's going to talk about dynamic behavior of pantograph delay differential equations.
Oh, and of course I wanted to say something about Thomas, but he already discussed with me everything that I know, and that maybe I think it's coming up. But if you forget something, then I will.
Okay. Okay, so thank you very much, and thanks for inviting me to come here to enjoy a few days with Martin and all of you. Fortunately, I could not come at the beginning. I came on Tuesday night just for a good start with the Gambay. But okay, I'm very happy to be here. And yes, I will try to say, okay, the title of the talk is there. I will talk more later. But first about the history of knowing Martin. According to my record, we unofficially met in Azores in 2011. I don't have picture with him because it was unofficially. I mean, he was there, I was there. And we are in some pictures. In the group picture, I didn't find him, so then I didn't show. But the real one, when I met him, was in San Carlos in 2012, in February or so. He gave a talk, a course on time scale. And then we took part in the summer meeting. Okay. Then for that, I don't have pictures either. So, but the same year, that was 2012, so we coincided in Rochelle. And then this is the ceremony where some students received the award of Obada Prize, okay. Decided by Rofen, and then Martin handed to the participant the certificate. And I don't know what is the role of the bottle of wine there, but
I know.
You know. Okay, then later.
No, but wait, you have to go back. You recognize one person on there besides Ruben?
Yes. But I think everybody recognizes.
Really?
Yes. It's Jacqueline. Yes.
And the bottle of the table.
And the bottle.
Yeah.
And the bottle of the table.
But the bottle that was, he gave that to me, and it was the last day of the conference, so. Yeah.
Yes, then we coincide in other series of gathering organized by the this was in Maricel. And this is the picture that proves that we were there. Because I didn't appear in any picture, so I pushed Martin to prove that I was there in that conference, and he succeeded. He found somebody who took a picture, and I. So then this here, and then I will show this picture in Madrid in the IMS conference. But this is the first picture of the night. I cannot show you the last pictures. Okay. Yes. This is, you can see that we are still beginning. Okay. The money is on the table to pay and go to another place. And it goes to another place and another place. And in some places, there are very, very funny pictures. Okay. But let me show you just this the beginning. This was in Madrid, in the IMS conference, and 10 days later, we met in Wuhan. And then after the talks, it was a conference on Peter Clauden's 65th birthday. And then we went to some pub to have a little beer. Okay, so then we had one to start, but then we realized that one it was not enough for 3 people. This is compartment. And then we ordered 2 more. Okay. So after that, we have some picture from Brasilia, and here this is not very clear, but you can see here Alexandrino. Alexandrino and Martin were the 2 guys who came back to hotel late. I don't know how many we are more than here. Okay, we're open, but it is said that Alessandro had more than you
Of course.
that day.
Every day.
Okay, and this is already showed the video. Okay, this is Martin Superstar. They show more abilities than the usual one. And then after that, we could not travel for some years because of the COVID. But in any case, one day we were exchanging emails, Martin and I, and we said, hey, how can we meet now? What can we do? And then they said, okay, let us organize a meeting, online meeting, and have beer. But then Martin said, but it has to be in an emergency way. So then we arranged everything for the day after. So then this is what's called emergency beer Zoom meeting that was regularly taking place every week, at least every week. And the length of every meeting was undetermined. Okay? It depended on the participant. One day we were in some moment, one in Hong Kong, one in Europe, and Martin in the States. So Martin started at a good time to start beer. Is it about 10 in the morning or and finishes at 1 or 2 a.m. of the next day. Okay. Then this, no? And then now mathematics. So the idea of considering this pantograph equation that we will show you later is that it's an equation, a very simple equation, delay equation, with a proportional delay, but interpreted like a delay equation is non-autonomous, even if it's constant delay and the vector field doesn't matter. So then, for the non-autonomous equation, we need to apply a special theory, either the skew product flow, or the pullback theory, or the uniform attractor, etc. Right? So then, this is the objective that we tried to handle more than 20 years ago. It's just to analyze the global behavior of the pantograph equation using a non-autonomous theory for differential equation. But we only succeed recently. So then I will explain. So this is some background saying about the importance of delay equation, that it should appear in the modeling of many phenomena because the evolution depends on the past, etc. And different kind of delay can have, for instance, memory terms, can have variable delay, constant delay, distributed delay, and can also be state dependent. That Giacchini has worked this a lot, okay? But I didn't work yet. And then let me show you how an equation which may have a different kind of delay can be written in a functional formulation, which allows to develop a general theory to prove the well-Posner, the existence of attractor, etc. And then, for any kind of equation that we may find, we can set it in this format here, that I will explain now, and then you apply the general result. This is the idea. You have a general theory for delay equation, and then any kind of delay could be included in this formula. Okay, so then consider this reaction diffusion equation. Yeah? We have this memory term. This equation appears in materials with memory problem. And then here we have a constant delay and a variable delay rho t. It's a positive function which can be bounded or unbounded. Okay? The rho can be bounded if it's finite, or unbounded if it's infinite. So then, if we define, for a function defined from R to an appropriate Banach space, we can define the u sub t, which is the history of this function up to time t, or the segment solution. Okay? And it's defined like a function for negative values. Okay? And ut plus theta is equal to ut plus theta. So then it means that when theta goes from minus infinity to 0, the values here are all the values of the u from minus infinity to t. So this is the history of the function or the solution. We are talking about the solution of the equation up to time t. Okay, so when we have this notation, this equation here, which contains three kinds of delay, can be rewritten as a differential equation in which the vector field on the right hand side is a function of, in principle, of t and of the history. Okay. Then, how can we rewrite this into this formulation? Okay, so we need to define a function f, which is defined from t times cx, and cx in general is a family or a set or a space of functions defined from -infinity 0 into the Banach space in which we are having our evolution of the system. Okay? I will say more properties, but let us say a set of functions defined from -infinity 0. So then, let me define this f in this way. I pick one function from -infinity 0 into x and define like Laplacian phi at 0, integral from -infinity to 0 Laplacian phi here, f1 t phi minus h plus f2 phi minus rho t. I define this. Then, if I replace phi by u sub t, which is in fact the history and therefore is a function defined from -infinity to 0 to x, I replace here, okay? And then apply the definition of u sub t of s is ut plus s. So then I replace and put here, and I obtain exactly this equation. If I make the change of variable here, okay, then it comes from -infinity to t, which is the equation here. So then, this equation that possesses three different kinds of delays can be written in the general abstract formulation. Okay? One important point is that if we have, for instance, a differential equation with delay, variable delay, which in principle is autonomous because the t does not appear explicitly in the vector field, but appear in the row. Okay? Appear in the row t. But this equation, one may think, okay, the f is autonomous because it does not have the time variable. If I rewrite in the abstract formulation for the delay equation, then it becomes non-autonomous. Because in order to set up, to transform this into this form, we need to define capital Ft phi, like f phi 0, phi minus rho t, and if we don't have t here, how can I put t here? Okay. So then it's necessary in order to have here minus rho t that the vector field f depends on t. So then when we replace this by ut, obtain this, which is the function. Okay. So then some equation that for delay equation may seem to be autonomous, in the end, if we consider in the abstract functional formulation, they are not. So then, when we have some equation general in this formulation, we need to fix initial data as a function from -infinity to 0, because at time tau, okay, we need to know the whole history up to time tau in order to make sense to this term. Okay? The initial time, I need to know the values of the u sub t at tau. So then I need to know u tau. So this is how the problem is well set up. And then, as this is non-autonomous, then we need to apply one of the theories of non-autonomous dynamical system. There are several possibilities. The original one, we come back to the 60s, 64, 63. Sale and Miller defined the skew product law, which is somehow a trick to transform a non-autonomous problem into an autonomous one, but in two variables. Somehow appear a new variable. So then they have a dynamical system, autonomous, which is a skew product because both components do not work the same. Okay? One is a group and the other is a cocycle. This is the, and both together is a semigroup, is autonomous, but independently are not. So then later in the early 90s appeared the theory of uniform attractors, developed by Chepisov and Bisik, and also the theory of pullback attractor. The pullback attractor are related to the concept that Chebyshev and Bisek used as a kernel section are the same thing, but at the beginning were not recognized, but basically are the same thing. And the pullback attractor is a concept that appears as a consequence of the stochastic dynamics, of the theory of random dynamical systems, which started to be developed in the 80s in Bremen, in the laboratory of Ludwig Arnold and Hans Krauer, Dion Marfus, etc. And first, it was developed the concept of random attractor, and then this was the inspiration for the pullback attractor, which is for deterministic dynamical systems. So then, this is where we have worked more, my group, my colleagues, into the theory of random dynamical system and was non-autonomous dynamical system. And for the pantograph equation, we wanted to see if it was possible to analyze the dynamics using the theory of non-autonomous dynamical system that we know in the pullback attractor. So then, the first work that appeared, as far as I know, is this in collaboration with Antonio Langa and James Robinson from Warwick University, about attractor for differential equation with variable delays. Variable delays create non-autonomous differential delay equation, functional formulation. So then it was in the early 2001. And after that, there have been many papers dealing with the dynamics of delay equation, etc. But the theory developed.
Is there a reason why we have the open interval at tau in the equation? I mean, can it be semi-open, semi-closed? I mean, closed from tau and to the infinity?
Well, you mean the interval? Where
The interval of the equation.
No, it can be. Well, this is a general equation. It can be ODE, it can be PDE. For PDE, you can apply the theory, variational theory to consider, and then the value in one point is irrelevant. You can change. So then it doesn't matter if you close or you leave it open. Okay. So then this is the main reason. Like that. Okay. You can put top close. Then apply that you have continuity. But this Cx, I said, is a set of functions that will be continuous, etc. But then, if you are dealing with PDE, maybe it's a space L2. So then, if it's L2, the value is 0. For a function in L2, it's irrelevant. You can change it. Okay, so then, there are many papers develop general theory about this equation. But the problem is that the pantograph equation has a difficulty, you say after this slide, in which I'm explaining the usual kind of spaces in which the differential equation is considered. In this case, these two spaces can be considered. These 0 are the continuous function, so that the limit at minus infinity exists. The limit of the function exists at minus infinity or at minus rho if rho is finite. So then it means continuous up to minus rho. But if it's up to minus infinity, or we have some weight so that the limit exists. These are the main spaces used for differential equation with delay. Okay, in principle, one could use one or another, but depending on the delay one has, can be included in the formulation or not, because normally you impose some kind of condition, Lipschitz condition or growth condition, etc. Depending if you are working in one space or in the other, you can consider this case well posed or not. Okay? So this needs more explanation, but it is not irrelevant to take one or the other. Okay? So then, for instance, if we want to impose on the vector field which contain the delay Lipschitz condition, if you consider this space, you cannot include variable delay. You cannot prove that the Lipschitz condition is well defined. However, in this space, yes. But then in this space, you cannot prove there exists an attractor, and in this, yes. Because in this, it's hard to prove the asymptotic compactness. Then, let me explain now why the pantograph equation is so simple, but has difficulty to be considered within this frame. Why? Okay, the pantograph equation is an ordinary differential equation with delay, which has this variable delay. It's Qt. Q is a number between 0 and 1. This equation, people who model phenomena say that they somehow regulate how the electricity passes from the wire of a train to the engine through the pantograph. The pantograph is this arm that goes up in the train. This is called pantograph, and they touch the wire with electricity. How the flux passes, say that is modeled by this equation. Okay, we are mathematicians, but this is a simple equation. And then this equation is a variable delay equation, but unbounded. Okay. We can rewrite this, adding and subtracting t. We can put here qt, t minus 1 minus qt. So this is t minus rho t, and rho t is 1 minus qt. 1 minus q is another positive number between 0 and 1. Okay. So then, rho t is, let's say, pt. This is the delay, so it's unbounded, because when t grows, pt grows. Okay. So then, we can put the equation in this way. But observe that here in this equation, most paper you can find in the literature, if not all, the t is always bigger than 0. And the initial value for the initial value problem are set as 0. And as 0, because when t is 0, this is 0, you only need to fix one value, u sub 0. u0 equal u sub 0. Then the problem is well posed. You can prove a system of solution, etc. No problem. You don't need to know the history, because for t positive, when you fix the initial value at t equals 0, you only need to know u0. But what happens when we want to fix, because the problem is non-autonomous, right? The problem is this problem is written in this non-autonomous framework for dynamical system. If we are going to apply the theory of pullback attractor, I will explain later a few details. The pullback idea is to analyze the dynamics of the equation when the initial time goes to minus infinity. And then we look what is happening now. So somehow the pullback idea is to explain what is the evolution of the problem at certain fixed time t, having started progressively earlier and earlier and earlier. Okay? So from where we come from minus infinity up to now. This is the idea of the problem. So we need to solve initial value problem with negative top. But for negative top, if we start in minus 1, from minus 1 to 0, the t of the solution is negative. But when t is negative, qt is bigger than t. So this equation is no longer a delay equation. It's an advanced equation. Okay. So what can we do? We didn't know. Okay. We know for many years. We started to work on this in 2002, 2003, but we didn't find the key in order to analyze the problem. Okay, so how can we generate this? Okay, I will explain you one idea, which was the motivating one, but then we did it in another, a little bit way, a different way, which is more elegant and it can be somehow more reasonable. Okay, the idea is the following. For positive t, there is no problem. Okay? There is no problem. But when I fix an initial value t0, if t0 is positive, then I need to know the values of the solution before the qt,0. So then I cannot fix the value of t0 as 0. I need to know more values. But when the initial value t0 is growing, I need bigger values to be known. The interval increase. So then it's sensible to fix a function from -infinity to 0 as the initial value. Even if we will not use it. But for any t0 growing, we need to know more values. So we fix a space for all initial values that can be considered. It's sensible to consider that our phase space will be the function defined from -infinity to 0. And then at any time t0, we fix that. Okay? So then, this is what we do. And then for positive t bigger than t0, we can generate a dynamical system, a non-autonomous dynamical system. Let us say semi-dynamical system. Okay? Because it's only for t bigger than t0. I want for all t bigger than t0, not positive for all, because my initial time has to go to -infinity. So then I could define this semigroup, not semigroup, in process. Okay? Process or a two-parameter semigroup. This is called u1 t0. When I pick this initial value, phi 0, I assign the history of the solution up to time t. Okay? The history. U sub t is the history up to time t. Okay? So then I pick a function defined from -infinity to 0 and assign another function defined from -infinity to 0. This is the way in which the theory of dynamical system works. Okay? You need to define a semigroup or a process in a phase space which pick one function and assign another function in the same space. Okay? So then, this is good. I can define u1, which is a process for t bigger than t0, bigger than 0. Okay? But now, how can I do for the negative values? Then, for the negative values, we observe that our equation here, for the negative values, our equation satisfies when t is negative that this is bigger than this. Then let us look at this equation as a delay equation in which the delay term is this. Not this. This will be the final value and this will be the delay. So then let us call set t uqt and ut is set t. Then the equation somehow would be transformed in this way. And then this is another differential equation. This set equals this. And for this is correct because t over q is less than t when t is negative. Okay. So then for this, after now changing the initial value according to this chain, right? The problem is transformed that the initial value, new initial value should be set t0q, the new function phi tilde, which is given by phi 0qs. So somehow we transform the problem in one which is well defined because it's a delay equation, this, and then this defines also another process for this equation, because this equation is well posed, defined in this way. I pick an initial value and assign the segment of the solution of this solution up to time t. Okay. So then, when I come back to the original variables, I have that the u sub t should be this u2 for t0 phi 0. Okay. This part is for t bigger than t0, less than 0. Okay. Both variable negative. The u1 was for the both variable positive. But what happened if the t is positive and the t0 is negative? Then we define in this way. We define now a new uts like if both are positive, the u1. If both are negative, the u2. And if the s is negative and the t is positive, then u2 0s for the negative and u1 t0 for the positive. So I have constructed this operator, family of operator, we satisfy the process property. Which are the process properties? That UTT is the identity. This is the key. Okay? And then that we have that UTS composed with US top is UT top. Okay? So then, if both are positive, if all are positive, it's satisfied. If all are negative, it's satisfied. Only need to check if one is positive, the other is negative. But in that case, simply we obtain, in the case this, for instance, sigma is negative, and then we have the UD sigma, as this is negative, is U1, U2, according to this. The U2, as this is positive, this is negative, this is the U2. So then, this is exactly what we have, because this one is a process that satisfies the composition. Okay? So it's very simple to prove that what we have created here is a process. Okay? So then we can now study the asymptotic behavior. I mean, if this is a process, then we can study if there are absorbing set and there are asymptotic compactness property, and they have a attractor and the structure of the attractor, etc. Okay? So the foundation are already obtained. But observe that here, what we have done is to construct a new vector field. So our problem started with a vector field F, and I have constructed the F tilde. I didn't give you all the details at the beginning, but I didn't calculate the derivative of the new set with respect to t. I just put it. Okay? Yeah. When I did this, I didn't calculate here the derivative. I just put the derivative equal to this f, which is the new vector field. Just make the change of variable. Later I will justify everything. But in the end, what we are creating is an artificial function for the negative values. For the positive, it's the same. Okay? But for the negative, it's different. So then, okay, our problem coincides for the positive, which is our original problem, but we are using another model with a different vector field. Okay? So then now I will show you another way to handle the problem without changing the vector field. But what we change is the delay. Okay? As it is, we cannot do it, so we need to change something. Okay? But in this way, what we can do is, instead of qt, we consider a function var rho t, which is defined as qt if t is positive, and t over q if t is negative. Remember that this is what happened when I made the change of variable before. So in the new variable was t over q, because for t negative, t over q is less than t, because 1 over q is bigger than 1. Okay? So then we consider, instead of our original pantograph equation, we consider this one, which exactly coincides with the pantograph equation with the same vector field. Okay? For t positive. And for t negative, okay, it's another, it's the same function, the same vector field, but what's changed is the value of the delay, but at 0, both are the same. Okay? We have continuity of the rod. The rod does not have any problem that they may have a jump or something. The rod is qt, t over q, t equals 0 is the same. Okay? So we are extending the problem for the negative with this function. But this is well defined now. It's a delay equation, and then everything. In fact, the analysis that we have done is valid not only for the case of pantograph or t, but when rho is a function which satisfies less than or equal to t, non-decreasing, and goes to infinity for t goes to infinity. So it's a much more general. Okay. So then, explain this now. I have 7 minutes. Okay, now is the time of the details. But the detail I will give you roughly, because can be found in the paper, and it is appear. Then, now we have our equation that it can be set exactly in the general setup, and then we only need to impose one assumption for all the analysis we have done. Okay? Okay, we could impose an assumption for the system solution, another assumption, additional one for the uniqueness, then another for dissipativity, etc. But if we impose this only assumption, which is that x multiplied by f, the scalar product, is less than gamma t plus alpha, the norm squared of beta, y. With this assumption, if alpha plus beta is strictly negative for all t, then we are able to prove everything. Okay? I mean, a system, uniqueness, continuity with respect to initial data, absorbing set, and asymptotic compact. So this is, you could impose other weaker one for something, but this is a simple. Okay? So here the important thing is that the gamma has to be positive and bounded. This will appear later in other concepts that appear and need to be finite, the supremum of gamma, so it has to be bounded. Okay? And then alpha is the dominant dissipative term, should be negative. And the beta can be positive, negative, but if it's positive, cannot dominate alpha. Alpha plus beta has to be less than a constant uniformly for G. Okay, so then this is the idea. So the space we will consider is the one that I denote E gamma at the beginning. Okay. The notation is because one part is for one talk and this part is for this talk. But the notation in the paper is this one. C gamma 0 are the continuous function such that the limit with respect to this weight E to gamma 0 s x. Gamma 0 is a positive number that we fix, and then it doesn't matter how big or how small, we fix one positive. And, okay, so then the crucial result is a result of the Hallanite type that is very helpful in the case of delay equation. Okay? So then first we prove one Hallanite inequality for this differential linear equation with delay. This is somehow the yt will be the norm of the solution ut to the problem square. With later we multiply by the equation by the vector field, then we obtain a differential equation and the inequality bounded the sum term. And then when we have that, then we can obtain estimation of the solution for the growth, etc. So this is the Hallanite. And it is proved that if we have this equation, this is the initial value, then with the assumption that we impose in H1, we have that the solution of this inequality satisfied, which is bounded by gamma star sigma that we add. And the gamma star you see is the supremum of gamma t from t0 to plus infinity. And then this is for every t0. This depends on the t0. If I want to apply this for all t0, if the gamma is bounded, automatically I have it. Okay. And the d hat is the norm of the phi 0, the supremum norm. But the space in which we are working has in the norm the weight into gamma 0s. So it's not the norm. But fortunately, is this and not the other, because otherwise we can obtain dissipativity. I will tell you. This detail is important to know. Why here appear the norm in the supremum norm, and we are using the norm here in the space, the norm with the weight. Okay. So then, this is the first point. So the solution can be bounded for all t bigger than t0, depending on this variable. Then, with this result, we can prove existence and uniqueness of local solution, just applying the theorem in the book of Ino Murakami Naito. Just require local Lipschitz function, but the f is C1 in all variables, so it's local Lipschitz. So then, and then for the global system, we need to prove that the solution does not explode. Okay. So then, we do the computation, apply the condition, is 1, and now apply the Hallanite inequality result, and can be obtained this, after all this computation. The norm gamma 0 contains the term, the exponential term. We need to multiply, divide, select, take supremum, okay, and obtain something which is the problem. Once we have for the xt, we need to prove for the exact t, for the segment of solution. Because later, the semi-group, this process, sorry, is the segment of the solution, but not the solution. So then, this also can be proved exactly in the same way. Okay. Once we have that, we have the continuity with respect to the initial values and the uniqueness, which is also a consequence of this. Is the same type of computation. And now, once we have the well-postness of the problem, we define the process, and the process has to be defined as the solution of the problem. In this case, the bar row allows us to have well-postness directly. We don't need to do strange thing, but somehow, once we have this defined the process, in order to construct it effectively, we need to do the change of variable. For the positive t, it's the same as before, but for the negatives, we do the change of variable. And here I calculate the derivative. Okay. In the previous motivating idea, I did it. But here, that was the idea, but this is the proof. Okay. In the proof, one has to be serious and calculate the derivative. Okay, I calculate the derivative here and obtain this f tilde, which contain here this q outside, etc. And then, exactly the same, we can define the process in there. Okay? But this is correctly proved. The other was just the idea. So then, when we have this, the next one is to prove the system of attractor. That was the objective at the beginning. So then for that, one need to recall, but I will not do it here because I don't have time, the idea of the pullback absorbing set or the forward absorbing set. The pullback means that we start in some bounded set, okay, of initial function, and there exists an initial time such that if for all initial time earlier than that, at time t, you are inside the set, the absorbing set. The absorbing set depends on time. Okay? This is the idea. And also the asymptotic compactness is the same. If we pull back, the initial time goes to minus infinity for every sequence and the initial value is bounded, then there is a subsequence which converts. It's asymptotic. So then, in this case, we can now define the pullback attractor or the forward attractor. Pullback attractor is the same. As the initial time goes to minus infinity, the solution approaches the family, which is compact, invariant, and attractive in the pullback. Okay? If it's forward, it's the typical definition. Okay? When t goes to plus infinity, approach the attractor. But the difference and the main reason why we use pullback attractor and not forward attractor is that for the pullback attractor, when you have that there exists a pullback absorbing set and you have a pullback asymptotic compactness, there exists the pullback attractor. But for the forward attractor, it is not true that if you have a forward absorbing set and forward asymptotic compactness, there exists the forward attractor. This is not true. So then, somehow the generalization of the similar theory is given by the pullback idea. So then, in our case, first we prove this inequality, which provides me the system of absorbing set. Because remember that the first lemma we proved, we obtain this same inequality, but with dt, only dt. But to have absorption, I need to have something that multiplies this dt, because dt somehow is the norm of the initial value. Something that goes to 0 when t0 goes to minus infinity. And I can make this be small, and then maybe a multiple of this plus some epsilon is absorbing. I mean, the solution enters there. Right? So then, the idea is that we need this. How appear this? Because we are using the norm with the weight, with the gamma 0s, okay? And the previous estimate we obtained in the other lemma was with the supremum of the initial value. Okay? Remember I told you the d tilde here, what's this? Here, this d tilde is somehow the norm of the phi 0, the initial value, but does not appear any exponential here. So I cannot have absorbing set because this depends on the initial value. And I want to know that for any initial value, this goes to some bounded set which does not depend on the initial value. So then, because we use that, now we can obtain in this lemma this term here by redoing the computation, and then the term that contains that we can analyze. It's a tedious analysis, but that can be done, and obtain this extra term. Then this extra term implies that 2 times the gamma star over delta is the radius of the absorbing set. Forward and pull back. This is true. Okay? It can be done because it's t minus t0. So then it's forward and pull back. And also allows to prove the asymptotic compactness forward and pull back in both cases. But with the forward, we cannot prove the system of attractor. But with the pullback, yes, because there is some result due to Peter Kloede and Thomas Laurent from Germany. And then using that we satisfy the pullback absorbing set and also the asymptotic compactness, we can prove the system. But still is open the analysis of the forward attractor. It is very likely that under some other condition it can be proved. And also we are studying the system of uniform attractor, which is a different problem. So let's stop here. Thank you very much. Happy birthday, Martin.
Thank you. Oh, then I ask you a question. So, because in the discrete case and in the timescales case, people also study pantograph equation, but as you said, all of them for t greater than or equal to 0. So I think in timescales there's no pullback attractor thing developed, but in discrete is, right? So can you do this?
In discrete there are theory for...
Yeah, so what about the pantograph equation in the discrete? Can you treat it in the same way?
Yes, it can be done, but we just finished this.
Yeah.
Still, we are trying to improve some point between, because there are some points that can be improved with the forward attractor and the uniform attractor. And also, after publishing the paper, we found a paper about the system of absorbing set of solution, absorbing set in the same dynamical system for positive t by using a change of variable, which transforms the pantograph equation into a constant delay equation.
Oh.
And now we are exploring that because that can solve maybe our point. But so far what I have done, need to impose limitation to the Q. And we need to avoid that because we want to have it in general. So then, but I don't know, I guess that for the discrete it should be possible.
Maybe somebody in the room is interested.
Maybe. Oh, Alessandrino.
Yeah.
He's done that.
So Thomas, thank you for a nice talk. And the uniform attractor will be uniform with the initial data, depending on the condition of data.
Wait. You know I am a little bit deaf.
Sorry.
I'm with that.
The uniform attractor will be in relation with respect to the initial data, or with respect to another parameter that you understand.
No. The uniform attractor is with respect to t. I mean, the uniform attractor is a compact set which is not invariant, but attract the solution forward in time.
Uniform with respect with the initial.
No, I mean, for every bounded set of initial condition, these are attracted.
And this condition will be related to the delta or to the gamma? If there's a bounded.
No, the absorbing set is the same. But then you need to prove the additional result you need to ensure the uniform attractor. Okay. You need some uniformity, okay? Especially in the t minus t0. Provided you get everything t minus t0, it can be wrong.
Any questions or comments? So let's thank the speaker. Professor Showing is our next speaker.
Maggie was on all the pictures that Thomas showed, except you were not in Azores, right? Yeah. So, and then she has all the stories. Maybe another one from Wuhan? Okay, so.
So Meg is going to speak about a larger competition model in stochastic environments. Thank you.
Well, first of all, thanks to the organizers for the kind invitation. I don't have any photo to show because I know that I would appear in multiple photos that Thomas showed. I want to clarify one thing. Marty and I, we did not meet in the bar.
Really?
So we were all, the whole group were in Madrid for the conference in 2014, and then we went to Wuhan again, lots of nice beer night. The story that he may have shared with people is at one of the places, Mix Bar, one of the photo we took, they had unlimited beer Wednesday night, and the whole group were there. And then maybe someone drank too much. The week afterward, they don't have the deal anymore. Okay, and also I would like to apologize if anybody is expecting me to talk about neural network. I decided to change the topic because we had a tour day yesterday, so that talk may be too technical for the last day of the conference. And also that one, I don't work on timescales. That one was not really related to difference equation or math biology, so I picked this one, which is loosely related to difference equations and also with some application in biology. The outline of this talk is I'm going to start by motivating the model of the Lockley model to explain the ecological reasoning behind. And then from there, we will derive a diffusion approximation to capture the randomness of the environment. And then we'll show how we analyze the model by using a special case to species case. And then we generalize it to multi-species case after that. Okay. So the model background is we are looking at a region with multiple ecological species. We can consider simply this is a garden that we have two different flowers or we have two different vegetables. So each species occupy a certain amount of area of size. They don't have to be all together. It can be spread out inside the region. But then what we are looking at is the fraction of habitat, the fraction of size that they occupy. So the total amount is 1, and then each species occupy a percentage of the total size. Okay, so these are different species, and then we look at discrete time, a window of age. The age can change over time. And then so at each time interval, we look at how many of them, each of them died, and then how many of them then would be reproduced from there. So nu I is a very important parameter. This is the death rate of adults in the ice species during this fixed amount of time. So you can see we have these little circles. These assume that these are the ones that died out during a time window of age. And then after they die out, these spaces would be freed up, and then that is going to be occupied by the newer one, the newer generated species. And how does that happen? Okay. So after all of these spaces are freed out, then all the species are going to compete for the site as if if they're entering into a lottery. Okay? And then some of them may grab the space, some of them may grab the space elsewhere. It is a lottery in the sense that they all compete for the same limited amount of area, but it's not completely random because the one who is more likely going to win the lottery are the ones who are stronger at reproducing. So that is how we define. This is beta I is the net reproduction rate of the species during that time, right? And then the new site, so you can see the bottom here is all the new species born from the current ones. And then this is the total site that freed out by the dead ones. And we can look at the portion occupied by the I species multiplied by their birth rate. So the ones who have a stronger or higher birth rate is going to be more likely to win the lottery, and then they pick up a fraction of the size. So that is the original point of the model. It's quite straightforward. This is the fraction of the I species at the end of each time interval. That is calculated by the original one multiplied by the one that died out during the time interval. And this is a new site, new area that they pick up by entering into the lottery and by being able to reproduce. So this is a fraction of the whole thing. And this is the discrete lottery model, discrete time lottery model. Okay. And then when we are saying that the environment is stochastic or random, how we characterize that? We know that the reproduction rate may be random or stochastic, and we know that the death rate may be random or stochastic. And how do we characterize that? Okay. So there are multiple ways of doing so. One very typical way is to just perturb the original equation by some sort of noise. Okay. Assuming the birth rate and the death rate, assuming they are both deterministic functions, they just depend on time. It may be seasonality, or it may be in simplified model, they can also be just constant. So a lot of the work in the literature for such cases would perturb the equation, the vector field, by some sort of noise. I put a G, general function G here, because we just don't know how it should look like. Sometimes people perturb it by a multiplicative noise. So this depends on the state. Sometimes in biological context, additive noise doesn't really make sense, because that may make the state to go below zero. So this is a very general type of looking at noise, characterizing noise, of perturbing it by some sort of noise, and then usually this will end up with a stochastic equation. And another way to characterize noise is we simply look at the system in a pathway sense. We consider the parameters beta and nu. These are the two most important parameters. We consider them as stochastic processes. And then, but the stochastic process is characterized by a driving dynamical system, theta t. And then each omega is a sample path in the probability space, and for each fixed omega, we have just a simply deterministic system. And so that for this, all the dynamical system tools, non-autonomous random dynamical system tools all apply here, and that gives us a very nice frame structure. And for this case, the Ito calculus all works. So what we are going to do today is we are eventually going to derive a stochastic differential equation, but we show a process of how to find out exactly this G, and we are also going to show how the vector field, or the drift term in the stochastic context, how that is going to be affected by the randomness. So why diffusion approximation? The discrete lottery model is mathematical natural, but the detailed long-term behavior is quite difficult to analyze. So what we do is, as h goes to 0, these are the observation window. I'm not sure how this is related to timescale, but maybe there's a relation. So when h goes to 0, we are going to pass to a continuous diffusion process by calculating the drift term and the diffusion term. And drift term tells us how the species evolve over time as the trend. and then the diffusion term tells us how that oscillates around. So this is going to produce a stochastic differential equation. And how we actually do it, so here's the probability setup. We consider probability space, and it's very important to note that the death rate and the birth rate, they both depend on observation window age. They are independent on each time, at each different discrete time. Okay. So then the process X, this is the unknown, forms a discrete time Markov chain. And that is important. And then what we're going to do is we will derive an approximation of the discrete corresponding to this probability. And this probability is given the initial state. For example, there is 50% of this area is occupied by a certain flower. And then what is the probability of this flower is going to occupy 70% of space at a future time. And we characterize the whole picture of this probability. So as always, we wanted to look at multi-species, but we always start from the simplest case. We are looking at two-species model, and then since the sum of them is 1, we are really looking at just a scalar model, it's a one-dimensional model. And how we do it is we first rewrite the system a little bit. Okay. So to rewrite the system, since we have just two species, instead of looking at them independently, we look at the relative strength of them. So that is how it's described by here. So we have the ratio of the reproduction rate of the two species, and then we also have the death rate, but it's opposite. So if this number is larger, that means species 1 is a lot stronger in both reproducing and surviving than species 2. So we combine them into one stochastic parameter that is going to tell us the relative interaction between the two species. So over there, we just define this way, and then we look at logarithmic scale. So we have this can be anywhere in between 0, above 0. And then, so we define this to be the stochastic process. This is one of the most important stochastic process for the whole model. And then because we are doing that, we also need to take care of these terms, and that is another stochastic process, which is this DI is a deterministic function that is the geometric mean of the death rate. And we look at the variation over there. So then we end up with the same system, but a different way of describing it. This is just a scalar system. Okay. And what we are going to do is how to characterize these stochastic processes right now. As I said in the previous one, if we are looking at the stochastic differential equation directly, we don't have any characterization of the parameters themselves. And then also in the random case, we have the dynamic picture, but we also don't have the probabilistic picture. So here we are able to capture the probabilistic evolution of the parameters by assuming the moment. We can do higher moment if we want to, but here we just look at the expectation of this relative strength parameter over the window of age. We assume that the mean is dependent on time. So that is a time-dependent, non-stationary stochastic. Okay, and then we assume that the variance depend on time, but then they all depend on the observation window age, and that is where eventually we can take the limit as age goes to 0 and then get an approximation from there. And then we are also looking at the covariance. So this tells us the stochastic behavior of how we describe the stochastic behavior of the whole system. And from there, we use just a definition of diffusion approximation. We look at the expectation of this change over the time, and then we look at the square. It's a pretty nasty calculation. So the student did all the work, and then we were able to derive a stochastic differential equation. And then so we were able to find an approximation of the drift term, of the diffusion term. We just do some simplification, and we get a diffusion approximation of the discrete time model. Now we have a continuous time model that is that is non-autonomous stochastic differential equation. And so what makes this system very different from what we normally seeing in the literature is the drift term is highly nonlinear, and also the diffusion term is also highly nonlinear. It's not just a simple multiplicative noise or additive noise. It has a very complicated structure, as we can see, with y is closer to 0 and y is closer to 1, and this function behaves completely differently. Okay, so here is the stochastic differential equation we get, and then all the terms are determined by the moment, by the variance, by the covariance of the random environmental parameter process. Okay. So what we can do here is we are assuming that all of these moments are continuous differentiable, so that we can do some analysis, and then all of them are bounded. But I just want to clarify that the boundedness of the moment functions does not mean that the process themselves are bounded. For example, we have a normal distribution with mean 0 and variance 1, it can still go above and below. So we are just assuming that the moments are bounded and have some sort of continuity, but the process themselves are still highly stochastic. So the first one is to just show that the system has a unique solution, so we were able to get that result. It's a very typical argument by we do a Lyapunov functional, and then we start from an interval between 1 over k and k, and we let k goes to infinity. And then we are able to show that the solution exists, unique, and always stay between 0 and 1. And that is very important because we are looking at a fraction, and they have to be between 0 and 1. And so that justifies the model that we derive make perfect biological sense over here. Okay. And then after that, we want to see what happens as time goes on, because eventually we want to look at the long time behavior. And so we were able to, under some conditions, I'm not listing the technical conditions over there, but we were able to see that under certain conditions, the expectation of, so starting from any different initial condition, and then the trajectories are all going together in mean, in that their average value are all going together. This doesn't matter where it starts. So just by looking at this, we only show that all the solution trajectories are going together, but we did not know where they are going to, because we don't have a constant, or we don't have a process in here that tells us where are they all going to. We only know that they are going to each other all together. So this is the result, the trajectories. And then after that, to get stochastic persistence, because even though we had the result that we know y is always between 0 and 1, but we don't know if they may approach 0 or they may approach 1. We don't know the case. So we want to show that under what cases that they are not approaching to either of the boundaries, and that is going to tell us that these two, none of them is ever going to die out. And then the typical technique used in stochastic differential equation, these persistence analysis, is if you are able to find a constant or some value that is between 0 and 1, and you are able to show that your trajectory oscillates above and up and down infinitely many times, and that gives you the result that they would never go to 0 or never go to 1. However, for this system, as we can see that everything is time dependent, so there's no constant in that way. However, we are able to find a trajectory. This is time dependent, so this is the y star t. And it's a time dependent function that would never touch 0 or 1. So it's a time dependent function, but within 0 and 1. And we're able to show that our solution actually oscillates up and down around this time-dependent trajectory infinite many times. So by that, we can show that, okay, the solution would never approach 0 or 1, and there's coexistence from that sense. Okay. So after that, then we get the stochastic persistence, and we want to look at the transition probability. That is, what is the probability of y taking up a certain percentage given the initial condition. And then to write out the equation for the transition probability is just a typical step of writing out the changes that, and that gives us a Fokker-Planck equation, partial differential equation. Okay. So having the Fokker-Planck equation, and the equation is here, and we have a one-dimensional equation, but then the difficulty was boundary degeneracy. So this G at boundary 0 and boundary 1, they take the value of 0. And I did not know enough partial differential equations. I still do not know enough partial differential equations. So we got stuck here for a long time. And then we also did not know there was existing result on one-dimensional case that you can just take care of it. So we went back, and then we did a direct approach. We actually did a change of variables. So this is why, and then we do this change of variables, and then we were then able to convert the 0 to 1 interval up to the whole real line from negative infinity to infinity. And then with this direct approach, direct change of variable, we do have one-to-one correspondence in the solution, in the probability, in the unknown. So as long as we are able to show the existing solution to this new system, then we can then change it, convert it back to the original system. So that is what we did. And then after we did that, I went to a conference and then learned that there was existing result, abstract result that can take care of this as well. Okay. So we got a new Fokker-Planck equation, and then we were able to transform it. We were able to show that the solution exists, and then we were able to show that the solution is also a probability density that satisfies all the properties of probability density. Okay. However, we don't have a stationary distribution, and we should not, because the environment, they are stochastic, and it's not stochastic in a stationary way where you have a constant mean, where you have a constant variation. As here we just don't. Everything is based on time. Everything is time dependent. And after that, we tried to do some numerical simulation just to visualize what we have got. See, this is corresponding to the first result. No matter where the initial conditions start from, all the trajectories always go together. They're still stochastic. We don't know where they are going, but we know they're all going together. Okay. And this is actually consistent with the pathwise convergence as well in the dynamical system framework. Okay. And then we also simulate and look at the variance. So this variance approaching 0 tells us that this is the variance between all the solution trajectories. And this further verifies that all the trajectories are going together. Okay. And then we also look at different samples. So this is mean of the difference. We have both convergence in mean, and we also have pathwise convergence. And in the end, we did some comparison with the deterministic counterpart, and this is the most interesting part, is if from the very beginning we don't consider stochastic environment, we simply look at the original equation, assuming everything is constant, assuming the death rate is constant, assuming that the birth rate, reproduction rate is constant, then we have a deterministic system. And interesting enough, for this system, there are only 2 steady states. So one of the species always die out. The system could only either go to 1, means one of the species occupies everything, or go to 0. Doesn't matter where it starts from. But with the stochasticity of the environment, we actually show that none of them ever died out under certain conditions. So this tells us the environmental variability actually can sometimes help promote the coexistence of species. And that makes perfect sense, because if the environment is constant, one of the species is always going to be benefit from that fixed condition, and then eventually will take over all the pieces. But if we have environmental stability, stochasticity, then one of them benefit from Y, and then the other one benefits, so we have this coexistence balanced out. the solution on the probability distribution. So at the beginning, it's a delta function because the starting point we assume that is deterministic, so we have just one peak. And then we can see that as time goes on, each of these cross-section at each time t, if we cut it out, it gives us the probability density function of the solution. So it gives us, for example, the probability of x taking 20% of space is this probability. So at each fixed time t, we have a distribution, and then this is a distribution over time. And also, as we can see, there's no stationary distribution. It varies over time. The whole profile varies over time. The variance and the mean, everything varies over time. So there's no stationary distribution. But there is also still some sort of distribution changing over there. Okay. And then after that, we try to say, let's try to generalize this into a higher dimension model. So we still start from the same difference equation that has n species, and then we just put it in an equivalent differential algebraic form because we know that the sum of all of them is 1. And we just take out one of them, and we actually set that one to be the reference species. Because the idea of the previous one is we compare the two species, how strong the reproduction is, how strong is the death rate is. And now instead of comparing two, we are comparing every species with one fixed reference species. And we see that if they're stronger in reproduction than this fixed species, or they die faster or not. So the idea is exactly the same, it's just now we pick one reference species and compare everyone else with that species. And we reformulate that the same way. We also look at the relative strength of birth and relative strength of death, comparing this to this reference species. Okay. So originally, we also wanted to do non-stationary environment. That means the expectation, covariance, variance of all the parameters should be time dependent. But then it got too overly complicated, and we did not have enough stochastic differential equation tools to even show the existence of solution there. So we decided, okay, let's do just the stational case. It's still stochastic. It's just all the moments don't change over time anymore. Okay. We again do the diffusion approximation. It's another complicated calculation, but in the end, we end up with a n-1 dimensional stochastic differential equation, and each of these is a fraction of size occupied by each species, and we have a highly nonlinear drift term, and we have a covariance matrix. But the difficulty here is we are able to, from the diffusion approximation, remember we have the g squared term, so we are able to derive the square of this matrix. When you have a single dimensional system, you have the square, you can just take the square root and get the diffusion term out. And when you have a higher dimensional system, you have a matrix that is the square of another matrix. So we were not able to get that because we were not able to write this g out explicitly. The only thing we know is the square of this, the terms. Okay, so we know the set of the equation, and then I mentioned the challenge here is that we don't have an explicit form of this one other than the square of the whole. So the first thing is, if we want to show that the solution exists for such an equation, we want to show that the covariance matrix A is non-negative definite. And that was already a challenging part. With our colleague from Auburn University, Dr. Ming Liao, he is a specialist in probability. So we worked with him, and he provided this very super smart idea of just showing that the A is non-negative definite. And then we can say that the SD is driven by well-defined diffusion matrix. And then that makes sure that we actually have a solution, and then the solution actually makes biological sense. So even the first step gives us a lot of challenge as well. And then after that, we were able to do similar thing by introducing the Abuna function and then construct stopping time. That is, we start from an interval and then we make it closer and closer to 0 and 1. As k goes to infinity, you can see it gets closer and closer. And then we show that the time that a solution ever exits from this interval is infinity. So that means the solution always stay in there almost surely. And this is a n multi-dimensional box. In one dimension, you just have an interval. And this is a multi-dimensional box that you don't really have the boundary of the box. And then after that, we also wanted to look at extinction and also coexistence. The technical details, I'll just omit all of them. So we are able to construct the condition on one specific species. When do they extinct? And it's extremely simple over here. And then what that tells us, remember this mu is the mean of the relative strength of two species. So if species 1 compared to the reference species, if it's strong, then this mu is positive. If it's not as strong as a reference species, this is going to be negative. But we have this term, which is the environmental variability. If the environment is changing very rapidly and largely, the sigma square is going to be larger. And just looking simply at this condition, the larger sigma is, then the more difficult this condition is going to be satisfied. And that means when we have very large environmental variability, then the species is more unlikely to extinct. And that's the biological interpretation over there. And it's all supported by mathematical proofs. And then for the persistent coexistence, the technical part is extremely challenging in the end, but then what we were able to do is we were able to show the condition under which at least two of them coexist. But we don't have a condition of one species who's not dying out. We don't know which species they are. We can only construct a condition under which that two of them, we don't know which two coexist. Okay, the other one can still. So this one actually involved a lot of analysis because of the different boundary part, and then we had to construct these intervals super carefully, and then use some manifold theory. I thank to the student for doing that. Okay, all right, and that is what I want to talk about today. We derived stochastic differential equation from discrete time model and using diffusion approximation. It is not the same as what has been done very frequently by just simply adding a noise term. We derive it from the stochastic properties of the processes of the parameters. And then for that, we have highly nonlinear stochastic differential equation, and then we were able to show the solution exists, makes biological sense, and we were also able to prove show the condition under which one of them die out or they all coexist. And with that, thank you all, and happy birthday to Martin.
Any questions or comments?
So you set up the discrete lottery equation and used it to make a limit to the continuous, and now you analyze the continuous.
Yes.
How about analyzing the discrete?
Yes. I don't know how. Yeah, I'm pretty sure we can do that.
And getting similar results, that would be exciting.
Maybe. So one of the reasons that it starts from discrete model is because one of our co-author is ecologist in University of Arizona, and they actually go out to the field and look at all of these species, and they can only observe over time because the system is intrinsically discrete.
Yeah.
It's just we don't know how to analyze it.
Well, because the continuous is easier.
Yeah, of course.
Any more questions or comments?
Well, no, I mean, I have more, but that's only after you admit doing it discrete. Because then you can also let the step size vary. You have the step size constant.
Yes.
Yeah, I would have asked the same. So in your case, the beta was a function of t. You could make this dependent on x, or it would be much more complicated.
Beta depends on t, but the whole birth rate depends on x.
Yeah.
So we still use, because every reproduction has to depend on themselves.
Yeah,
So we
yeah.
use the linear relation. You have a
beta
beta
x.
times x.
But you could make it non-linear with some competition term.
It could be.
Yeah.
It could be. Yeah.
But you think that you would still end up with a Fokker-Planck equation that you could study.
There's always going to be a Fokker-Planck equation. It's just not going to be the same.
And can I ask you, so the coexistence that you investigate, that's interesting, right? Because the argument is often when you introduce stochasticity, then you use oscillations, and then species get out. So the coexistence that you looked at was that the quasi-extinction idea, that you have to be above a threshold for a long time, or how did you define this?
Extinction?
Yeah,
So it's just the limit goes to 0.
yeah. But it's not, because there's something like quasi-extinction, right? That if you go below a particular threshold and you stay below for a sufficiently long time, you would consider that species to be extinct. Is that possible to do in this framework, or it would be too hard to analyze?
I think it is possible. It's just, here we just consider the traditional type of extinction, which we say that the natural log 1 over x goes to infinity, or goes to 0. And then so for two species, the extinction is characterized by one of them going to 0 and the other one die out. And for n species, we did it the same way. So we characterized extinction of the other ones take over. I think I like the idea of just looking at the lowest threshold and they are there, but they're not really there.
Yeah.
That may be very interesting as well.
Okay, so let's thank our speaker. So now our first talk after our coffee break will be changing with Professor Nicholas, because Professor Nicholas is not here yet. So it's Professor Geraldo Soares de Souza from Auburn University, and he's going to talk about historical account of some important facts in harmonic analysis and recent results.
Thank you so much.
Yeah? Okay.
Well, first of all, I would like to explain.
Yes.
Thank you so much for the invitation in here. I brought one little gift to the anniversary.
All right. Thank you.
And when I was invited to give a talk here, said, what I'm going to talk about? Mais alto, minha esposa e minha filha estão dizendo mais alto, mais alto. Vocês estão escutando lá atrás?
Okay.
Então tem que usar o microfone. Ok, e agora? Melhorou, valeu. Então, then what I'm going to talk about, and myself and Ed Quest, many of you knows him, and we decided to talk about some accounts of harmonic analysis, and I am going connected with dynamic system. Okay, I don't know if it's going to work, but I will try. Now, I am from the Zygmunt group. Stein, Pfefferman, Wilweiss, Yves Meyer, all those nice people. I am just on the bottom of the ladder. Okay? Then I am going to talk about few important results. I was worried how wavelet came about. it turns out that I was one of the protagonists on the creation of wavelet. So I am going step by step, going back to Hardy Littlewood, Marcel Rees, and so forth and so on. Okay? So let's go, let's get started. Okay, that's my friend Bohner, is already not with us, right? Bohner advised scholars speak to make at least 15 minutes of assessment of the entire region. They said, do you know how difficult that is? Okay, then that is stuff that we're going to see now. Okay? That's the motivation over there. We're going to get to wavelets. It's a very interesting story. Just a little detour from what you guys do. Okay? Now, Hardy introduced this space over here. Quite interesting. Lebesgue introduced this space. I invited him to come over here. Despite some protest, they decided to come. Okay? And that's two interesting spaces, and this was introduced by Hardy Littlewood. However, it was Frege that gave the name of Hardy space. Okay? Now, what the connection dynamic system? Look at it. This is our connection that we have for dynamic, for discrete system. The dynamic system, the unit plays important role in involved. So that stuff is connected over there in the very heavily, right? Then I invite my friend David Hilbert. It was difficult to get him over there. That is the Hilbert transport. The reason I put tangent over here, because I would like to give a notion of where the Hilbert transformer comes from. The Hilbert transformer comes from, if you have the Fourier series on the complex analysis, you have the real part and you have the imaginary part. And the imaginary part was called conjugated function. But when you make all the computation, that's what you have. However, tangent at 0, tangent at x, for example, is exactly the Hilbert transform. It's an equivalent to the Hilbert transform. Probably that's one of the most important operators that we have in analysis. But that's debate. Now, the Hilbert transform doesn't map L1 into L1. Is the operator, you look the Hilbert transform as a principal value, but doesn't map L1 to L1. And this becomes more excited and interesting, you see it. Okay? Now, look over here. Connection with dynamic system. All this over here is connected with this one. Okay? Then, now, this over here is the beginning of the creation of wavelength. Make it debatable, but it's the beginning. Why this is so? Because Marcel Rees, he proved that LP is invariant on the Hilbert transform. What that means? That means if F belongs to LP, the Hilbert transform belongs to LP. And this was the beginning of the game, okay? And from that, this over here proves that LP and HP are the same. Well, one is a space of complex analysis, the other is a space on the boundary. The whole point is you pick a function in HP, go to the boundary, you fall in LP. You pick a function LP, pick the Poisson formula, then you fall on the hard space. So that means LP is the boundary characterization of HP. HP is the analytical characterization of LP. Both are the same. I used to say that it looks like fox and dog. It looks like this. Okay. Then the consequence of this over here is the duality of HP is HQ. Exactly the same as LP with this condition over there. Then the problem is what? P is equal to 1. Or P is equal to 1, that was an open problem for many years, over 50 years. Everybody tried to connect in the computer the dual. The dual, the space of linear function, right? Okay. Now, I try to clarify this correspondence over here. If a function is LP, you look at this analytical function over here, okay? And this function is HP. If you pick a function in HP and go to the boundary, then you fall in HP. So they are exactly the same, okay? Okay, now open problem. This question took too long for us to try to solve this. What is the dual of H1? For many years, the eventual answer produced new ideas in new direction and harmonic analysis. This is important. In order to get to the dual H1, we have to create a new technique, and this open the gate of new ideas. Okay? Okay, let's move on. Okay, then interesting story over here. Okay, John Nirenberg from New York studying differential equation. Okay, introduce a space of function called bounded means oscillation. That's, many people introduce a space of function, but what's interesting is this over here. Okay, that's contained and is not equal. Because H1 is contained in L1. If you take the duality, the dual of L1 is contained in the dual of H1, but the dual of L1 is L infinity. It was proved that the dual of H1 could not be L infinity. Was something a little bit bigger. Okay, now you probably get the idea of what's going to happen, right? Then, two things happened. One was Ronald Koopman, a Belgian mathematician, introduced this function over here. An atom is a function, okay? Function, bounded, so the function is between two lines, okay? And then he gets the decomposition of function this type over here, and what this over here for? This over here to this makes sense. This representation over here is not unique. So this over here is not a norm with this representation. You have to take the if, okay? Then Koopman show the H1, let me go back over here. That's A space, okay? And that's the norm, which become a Banach space. Then Koifman proved in Studia Mathematica, they are equivalent, and that is considered to be the atomic decomposition of H1. This was the beginning, or at least one step forward to get what we want to get, okay? And the Pfefferman, before Koifman, before Koifman proved that the dual of H1 is BMO, that's Pfefferman. We want to see some picture of it, yeah? Pfefferman, okay? And then that's interesting. Then Koifman comes with this result. To me, this result, I can prove easily the dual of H1 is BMO. Easily. As a matter of fact, in conversation, I have some letter I will show it to you, where Yves Meyer said, I thought rather this was a simple way to compute the dual. Okay? Well, before I continue, this problem over here was open for a long time. Charlie Pfefferman had about 21 years old. He won the Nobel Prize quotation field medalist in mathematics. At the same time, he was given the position of full professor at the University of Chicago with 1 year, just because of this little discovery over here. Let's continue. Okay, now, that is the connection with the dynamic system. Okay, here we have, it's quite interesting, right? Okay, then Geraldo coming, de Souza coming to play, right? What is a simple atom? There is a little story over here, a lot of stories, okay? I came to do my PhD in the University of New York. Who was giving a talk? Lennon Carlson from University of Uppsala, and was talking about Pfefferman duality theorem. Then he looked to the atomic decomposition. I was a student, I spent 15 minutes to try to give an example of an atom. This is an atom. And the natural question is this: can I take atom from the space A and replace it by a special atom and get the same result? Okay, the answer is no. But I spent 15 minutes to get this animal. Then that's the space that I introduced in my PhD thesis. This is the space of a special atom, which Yves Meyer in his book called the Sousa space. He was the guy who baptized. Okay, then I take the decomposition, the same decomposition that we have for Koifman decomposition, except this are a special atom, this type over here, right? And that is a norm, okay? Now the question is, you have this new space, what do you do with that? Okay, what do you do with that? And that's what 1980, I introduced this PhD. Now comes the big part. It's a Banach space that, you know, this is contained on this. The question is, can you get a reverse inequality with a constant? No, we cannot. However, life gets more interesting because the dual of this space P1, the special atom, is Sigmund, the derivative of Sigmund space. Then I was very happy when this happened, okay? But for those people who are familiar with Zygmunt space sum of function, there is no derivative, then you have to get some convolution in order to do this. But that's beside the point. Okay, let's continue over here. Now, again, an opening problem for a long time was this. Look, this space over here. Okay, the derivative analytical function. Okay, and this is over here plus something is a norm. Okay, and this space over here becomes a Banach space. Then J, this space over here is the analytical characterization of the special atom space, and this was the opening problem for a long time. You have this space of analytical function in here. When you go to the boundary, then what that is? Then what you get is the special atom space. Okay. Continue. Long-standing problem was obtain the real characterization of J1, and we did this. Someone mentioned Gary Sampson, and this problem over here, I solved for Gary Sampson. Okay. Then there was a conference in Sicilia, Italy. And me and my supervisor was invited to participate.
Which year?
Huh?
Which year?
This was 1978 or 79, something like this. I could not go because my wife was pregnant, expect our third baby. So O'Neill went over there, okay? So, even here was sitting just like this fellow is sitting in there, and asked the following. This is a dialectical interval. The dialectical interval plays an important role in analysis, okay? The question was, in the definition of the special atom space, can general interval be replaced by dialectical interval? Quite interesting question. We don't know what Ibn Meir had in mind. You see it. Then you have the half function. Is invited here. That's the half function. Okay. So Ibn Meir notice, okay, that this half system, which is the orthogonal system, in the L2, is a base for L2, okay, would be written as one single function. What the function? You pick the intervals A1, you split in half, 1 and minus 1, normalizing L2 normal. That means pick the function that's 1 and minus 1, squeeze and stretch, and you get. So, let me move. So that is the half function. Now, I'm going to rewrite this half function. Over here you are. The half function can be written as one function. And the function is pick 0, 1, half 1, half minus 1. So if Meir asks, can you replace the function who generate the whole half function, like the trigonometric system? The trigonal system is generated by one function, e to the ix. Then he said, can I take this function out over there and put any function? And that is what we write. okay? Now, the problem with the atomic decomposition of coefficient, in the special atomic decomposition of Sousa, the system is not orthogonal. Then you don't have a characterization of the coefficients. But you can see this over here is the special atom space based on diagonal interval. Then because the diagonal intervals form a orthogonal base, you can get the coefficients. Okay. Then, they is not topological equivalent to H1. This observation led even a year to think more deeply about Haas system. Can you replace the generate function of the Haas base by another function still be, and that is the creation of wavelets. Okay. After that, everything moved. Every area of mathematics, economy, music, wavelet was there. For impact muito very big. And it was interesting because I said, the atomic decomposition who led to the wavelet is one of the most important creations of the analysis nos last few years, okay, 30 years, 40 years. Then I was invited to give a talk in Moscow, okay? Then, when I get over there, I had about 100 people in the seminar, and I would look at and say, that's the place where it come over off. Then I feel some shilling bones, Then when I said the atomic decomposition was one of the most important, they held glucose. Okay, so the guy who was complaining did not speak a good English. Took 10 minutes. I was about to pull in my pants, but the guy who had invited me, he said, "You talk to Dr. Sousa later on." Okay. Well, to make a long story short, when I came back, I wrote a letter to Yves Meyer, which I'm going to show the letter to Yves Meyer. And let me add something. I was invited to be a review for the Academy of Science of Russia. Then I wrote to them and said, who had recommended me? You guess who was, right? The guy who was questions my saying that 30 years of, advancing analysis was this. Okay. Okay, let's keep moving. Wavelets and dynamic system. Chaotic time series. With scalar analysis, blah, blah, blah. Unlike Fourier series, when wavelet localize both time and frequency, which doesn't happen with Fourier series. Okay, this was my supervisor, Richard O'Neill, that was a student of Zygmunt. Okay, and the interesting one, Lennon Carlson gave a talk. We walked together, leaving the room. Then I told Professor O'Neill, I spent 15 minutes or more to try to give an example of an atom. And he said, me too. I said, are you a new student over here? I said, yes. Can you be my student, PhD student? I I said yes. Okay. If in a year hear about this idea, pursue a related question about her function. Correspondência on you behind the story. Okay. Broad's lecture. Wavelet become a striking example of how question harmonical knot generate new theory and major cross-disciplinary. Okay. Now we move. Now we know how the wavelet was created. Now you know the impact that wavelet have in every branch of possible. Okay. Then Louisine, this is interesting guy. So Louisine conjecture. If F belongs to L2, then the convergence almost everywhere. You know, this conjecture was 1930, and 53 years, nobody solved that problem. Okay? Now let me tell you how this came about. When I was in Russia, I asked one of the big professors over there, how come Louisine did not solve this? Because he was a very smart guy. And he said, he had a proof, but he did not believe in his proof. That's not Then come Alberto Calderon. Alberto Calderon is an Argentinian mathematician. He was in engineering. Anthony Zygmunt went to teach a class in University of Buenos Aires, and Calderon was the best student in the class. So Zygmunt comes, Alberto, do you want to come to the United States and do the PhD with me? Calderon said yes. So it became the most powerful duo in harmonic analysis. Alberto Calderon, Calderon Zygmunt decomposition, Calderon Zygmunt operate, blah blah blah, all those nonsense stuff. Okay? Now, look what Calderon did, which not many people knows that. Okay? That's the partial sum of Fourier series. And he transformed this in an operator. Okay? Then he proved that this operator, which is not linear, quasi-linear, is bounded. Okay? If only if it's not if the Fourier series converges, the Fourier series of a function L2 converges almost everywhere. So I asked Zygmunt, I said, when Calderon did this, and he said, look, I was in my office, Calderon came and said, I think I have the proof of the Louisine conjecture. And Zygmunt is always calm, sat down. Calderon went to the board, and Calderon proved its convergence is a function in L2. Converges almost everywhere, if only if this happened over here. Then Zygmunt said, you didn't prove neither this. And he said, you proved it. Never did. Then come Leon Carlson in 1966 and proved that Max L2 and weak L1. Richard Hunt, which was a student of Unifies, was a student of Zygmunt, proved that it maps LP into LP. Okay? Let's go to the next. Leon Carlson. What's interesting in Leon Carlson is Leon Carlson, he won the Obada Prize for 3 problems. The the convergence of Fourier series in L2, Kakeya theorem, and the Corona's theorem. That was how important this is, okay? This over here, people said that Carlson was a problem solver. If you have a problem, computation, give to Carlson, they will do, but not a person to create a new theory. Much of the problem that he solved, Kakeya theorem, that's in the equation, the Corona's theorem is complex analysis, an open problem, and the convergence of Fourier series. But let's continue our life. Come back with the dynamic system. Reconstruct quasi-periodic motion, spectrum light flow, Copeland operating net, Carlos theorem, guarantee convergence for block analysis. So, harmonic analysis is everywhere. Okay, now comes the Sousa. Okay, so I looked what Calderon did, what Lennon Carlson did was, if he maps L2 into L2, the convergence almost everywhere happens. So I noticed that you don't need maps L2 into L2. If you prove that a map L2 into some space, that is enough to guarantee the convergence of the Fourier series. As a matter of fact, after Carlson proved this theorem, Charles Pfeffer proved that this operator, maximum operator called, maps L2 in L1 from L1 weak. Weak L1. There was a problem with the proof, but there was. Then I wanted to defend because I was studying on this slide. This is a function, a space of function, which is contained in LP, okay? So I would like to show that this using the Calderon method to prove that the function over here, the Fourier series converges almost everywhere. This was a space that was introduced by Gigi Lorentz in Austin, Texas, in the 50s, and a very important interpolation of operator that was crucial. Okay. Then there we have the relationship. You have the relationship with LP1, okay, and LP alpha is the Lipschitz class. Now comes the theorem. The Susan in 4 and 8 proved that maximum operator maps LBP into LP1. Therefore, it have the almost everywhere. Also, I proved in 2009 that indeed maps LP1 into LP1. Remember what LP1 is, right? That's LP1. If someone are familiar with Lorentz space, you have the big space over here they call weak LP space. On this end over here you have LP1. In between you have LPQ space. Okay? This is probably the most important among the LPQ space, that's Lorentz space. Okay? Now, why this is exciting? Because this rearrangement function over here, there is no power. It's easier to handle, but anyway. Then the conclusion is, if F belongs to LP1, then it conveys almost everywhere. Now we can use interpolation theorem to map LP1 in LP1. Okay, then you have connection with the dynamic system. Okay. Atomic energy decomposition. Okay, that's what the letter that I sent to you in the year about the Russian mathematician. That was the letter that Ibn sent to me. Over here, he said, I have a vivid memory of some discussion with Anton Zygmunt about the relevance of the duality scholar. That's happened 73. Zygmunt as usual, very prophetic, said he thought the atomic decomposition was more important than the Pfeffer theorem. Then Irmeyer said, I was thinking that the coefficient result was one way to write it wrong. I was wrong. Okay, let's go to the next one. That's an interesting letter of Paul. Okay. I always ask it. Paul was a friend of mine. Okay, I ask the people what this question means. I put for you guys. Now, this over here is with Weiss, and I was telling is this. I gave a atomic decomposition of LP1, and I was telling you did not solve this problem because you interested in interpolation. Now, here I have Zygmunt, I just fresh look at the time. Okay? That's your Gonzaga, who is the student Zygmunt. And on this conference over here, like I finished my PhD, I came to Zygmunt and I showed that the duo of the special workspace was the Zygmunt class. And they said, well, very interesting, asked some question. I said, can I take a picture of you? And he said, we are related mathematics. Yes, you can. And that's this picture. Then, for 25 years, I organized a series of harmonic analysis conferences in the related area in Albany University. And one weekend, I invited Charles, that's Robert Pfeffer, and that's Charles Pfeffer, and they call a weekend with Charles Pfeffer. I have granted National Science Foundation, and the money was not enough because I have 125 people. This is Steve Meyer. Thank you so much.
Comments, questions?
I'd like to thank you for your awesome talk. I learned very much, and for your contribution to mathematics, especially to harmonic analysis. That was very much clarifying. Thank you very much. Any other comments? Let's thank Professor Geraldo.
Hello. So then, your talk is starting, right?
Somehow, I don't know.
Wait,
A lot of beers.
You two wait a little bit. For a while. So now we have Professor Nicholas Osterman. Yeah. From Adelaide University, and he's going to talk about unification of fractional time scale. Now.
Okay, thank you. Yeah, so this is Nick Fuster Young, and well, I know him for a long time, but before I knew him, I knew his advisor. His advisor is like the, let's say, the beginning, from the beginning of time scales. Christis Delle is in time scales, and so he was our base in Australia for time scale. and came out to Nick, and we met many times. Also, he visited once Rana. We had a good time in Rana. He gave a talk, and then we even went for a weekend to Las Vegas.
We won lots of money in Las Vegas. Yeah. We might have used a little bit of time scales when we were there at the machines, but we definitely had a lot of beers. Now there was definitely a few beers in this talk, that's for sure. But I do want to start with saying thank you for everyone that organised, so Tom, Sabrina, Jacqueline, and thank you Martin for having me and putting up with me for so many years still. I thought I'd just go out on a limb a little bit and talk about timescales, but we're going to completely talk about fractional timescales today. And what we're going to try and do, and try and tell you via geometry, is how we can potentially unify fractional timescales. So have a definition which allows us to move between general timescales and in a closed form. And it's quite interesting, and in my opinion what we're going to do is just, well, actually I'm not going to deal with the nublar case, I'm only going to deal with the delta case. Reason being is, in the delta case we push forward and we have inherent properties which actually come induced from the kernel of a convolution in terms of the delta case. But in the nublar case, in the geometry of it, it actually becomes sucked in to the kernel. And we don't have a shift in the domain of what occurs. It actually gets eaten up by going basically plus and minus in terms of the shift. But in the delta case, it does not. And it's like when you integrate and you're moving forward, you lose your steps that you're counting. Okay, so the foundations of timescales goes way back, as you all know, and I will go through this very quickly. So you know there's Helga and Martin and Alan and everyone else that's here who will work on timescales. And at the core we want to define all the classical results in terms of on timescales. So from the continuous case and the discrete case onto timescales for dynamic systems. Now obviously there's a very important result. One of the hinging results is that we have the exponential function. And that is probably the biggest part of timescales itself. And here are just two examples of what they look like, in case you don't know, on the reals and on the integers. And you know, there are plenty of things that people have done over the years, moving forward. You know, fractional calculus has been around for a very long time, you know, dating back to even Leibniz, and it's evolved. The continuous case really only came out maybe in the 80s and 90s, being developed a lot more, so on the reals. And discrete case only was what, 2005 I think it was the first. And then most of it came out after that, 2007, sorry. And then most of it came out with Goodrich and Peterson, defining what it looks like, the delta, nublar, and quantum case for discrete fraction. And then, you know, there's been some great attempts in terms of the general timescales. Svetlin did a great job in trying to generalize what there is, but had disregard for the domains that were there in terms of the definitions and understanding maybe a little more on the geometry of what might be occurring. There is still one completely unanswered question when it comes to this is, okay, what is the inverse Laplacian of z to the minus alpha, where alpha is positive? That is still a question which still becomes unknown, but still needs a lot more development. But can we frame up things in terms of a geometric approach? And there's plenty of applications that go through in timescales, and this is why it is such an important field for us to look into and actually develop theory around it. So just for anyone who's not sure, I stole these from Martin's book. These are just different timescales that you can have a look at, okay? And in this case here, you know, you've got your reals, integers, that's it, your polynomials, and then you've got your hybrid. We've got a combination. Now, I want to go a bit back in time for the first time that I ever met Martin.
Who is the one on the left?
That's me. I can't remember, I think this would have been 2009, 2012.
Maybe.
Yeah,
It was for Peterson's retirement.
it was Peterson's retirement.
And that's a Sierra Nevada Pale Ale.
Yeah. So I had to find a picture with a beer in it, and Martin holding a beer. So I thought we'd go all the way back to the first time I ever met Martin. And then we didn't see each other for many years. Maybe, 6 years? I won't show any more beer pictures, I promise. Just to go back and think about, in case anyone's not sure, here are some of the key operators that exist in timescales. And I'm sure most of you know, so I don't want to spend forever going through everything here of all of this, because there's a lot to go through. But if anyone has any questions, please ask. So one of the challenges here in building any framework, and building a framework for the delta fractional case, is that it jumps. Now if we just think about the discrete case, we look at it and go, okay, well it jumps, and it jumps actually by the order of the fractional power. Okay, so it keeps jumping those domains continuously. Now the question is, how does this look when we move to different timescales as well? We move to hexagon. What does it look like? Quantum. What does it look like? These are the questions, and you'll see, as most of you should know, is if you're thinking about quantum, you're moving in the Q case, so you're moving Q. And then how does that play on alpha, on the order of the fractional order? So can we geometrically sort of interpret what's going on? And can we come back to sort of the foundations of timescales and think, okay, well, if I'm going to take a derivative, even in the continuous case, or I'm going to take it, move up to the discrete, or an arbitrary timescale, we're always thinking about the graininess of our timescale and the next forward step. So can we define a fractional shift using a projection of the timescales back to the ordinary timescales we're on? So thinking about, if I've got my timescales, TA, you might just want to think about ZA, and then we project that and shift it by the graininess onto another timescale, say we call T alpha, where alpha is the order of the fractional power that you're going to be, say, integrating overall summation. And then we look at that and go, okay, we've got that, moving up to there, where now we can pull back and come back again. But can we go back and look at all those classical results now, thinking, forget about the order, the power, which is more the depth of what you're integrating and jumping, and just consider it, instead of just as a fractional number, go back to the original timescale in terms of the jumps. So let's say you're on the integers, and you want to go up by an order of alpha, we project, we go to T alpha, where we're going to be, but then we actually do everything in TA or ZA, where you're originally. So I thought it would be good if I just gave a couple of very easy examples. So in the continuous case, if we are looking at the rim in Louisville, or even Caputo, but we'll just concentrate on the rim in Louisville here, and we just thought about, okay, what is the alpha derivative, so say to a half in this case here, of the function, of a power function, which we will eventually call, and as we've generalized, we call monomials. So if we take the half derivative, which goes on the first result that we've done, of t, just t, then we can see that we end up with a gamma representation of gamma 2 on gamma 3 on 2, t to the half. Now, as many of you know, and you've given talks and gone through, you know that this is starting to form a, what do they call it again, Tom?
Huh?
What are the falling monomials?
Falling powers.
Yeah, so falling powers, but I forgot what the name. What's the symbol?
HK on time scale.
Yeah, that's right.
Underscore.
Yeah, no, what are the symbols?
Block hammers.
Block, yeah, so
Those are rising.
yeah, what's the one that goes down?
Falling.
Oh, it's just falling.
Falling
I thought
hammer.
maybe there was another name.
You can write as a puck hammer, but I don't like to.
Yeah. So we're falling down, as you can see. Now, if we look at the function, if we look at, say, in the discrete case, and we start dropping, again now in the half, we see the same sort of thing happening, same representation of what we have. Except now we have a falling polynomial. Okay, so we now have this falling function that's dropping down. And this is this all stems or comes out of actually the fundamental definitions of what we have on timescales. So let's go back to the grid book and just remind ourselves, what is the definition of a delta derivative? Okay, most of you should all know this. But what we can see here is we're looking at how we jump. And if you go back to the foundations of calculus, we are jumping, or we're moving in terms of time steps, with sigma t minus t, which is the gradient. That is where we're moving. Or if we're in continuous case, then we are concentrating. Right? So we have the gradient s, which is defined by t. Okay, so if it's right dense, then it's 0, and we're just then looking at those infinitesimal jumps. And this is sort of where the motivation comes from. Now, in the continuous case, if we start thinking about conformal mappings of where we're moving, these are the two conformal mappings on R and Z. So in this case here, we can see that we have t on 1 minus alpha coming out, and again, t on 1 minus alpha coming out. Okay? And this is quite powerful. Right? In terms of where we're moving, in terms of what is going on here, this is forming part of the kernel or the developing stages of how we actually integrate, or actually differentiate in this case. So again, I want to come back and just back to the green book and have a look at this definition, which is if we've got a right dense continuous function, it's antiderivative, as you can see, we'll call f hat or f triangle, blah blah blah. Delta integral is defined by this, and we can split what we're looking at here by the summation, right, or the integral here. So the summation, the gradient times f on discrete times f, where the right scattered, and then we have our right dense component as well. So in a simple form, you could just have just right scattered, or you could just have right dense, but we could have a combination. Another very fundamental definition, which I won't go into in huge amounts of detail, is the exponential function. Now, on the timescales, the exponential function, EP, is defined as the following. And this is where we want to come back to and stay. And we want to be able to find a definition such that it's going to satisfy this in a general case. And form up our mid-Leffler functions that we'll have at the end. So can we have a generalized mid-Leffler function, which is going to solve this equation here, where P of t is a constant. So in R, we have the standard exponential function, which will solve this, and in Z, in discrete time, we have the product, and too much. Classical definitions of fractional calculus on continuous set are the following, and the Riemann-Lewis Caputo. I won't deal with Caputo in this case here, but I want you to just remember what the Riemann-Lewis definition is as we go through today. And then also this comes from the Peterson and Goodrich book, which is the definition of a discrete fractional sum, okay, and differences. So the sum itself here, we can see the sums from A to t minus alpha. And then we have the kernel here, which is a squalling monomial, where t is defined in the shift. So we're shifting in the domain by alpha, the order each single time. And that's really important. So every time we take a delta sum, we're shifting alpha, or whatever the order is. And this has a semi-group property as well, and it's well formed. Okay, it's well defined. Now, this is the derivative, or the difference if you're going alpha, and you actually go backwards. So you're moving forward and then you're moving backwards both. And that's what if you're thinking about this conceptually, just imagine you're on a time scale, on a discrete set, and all you're doing is go, okay, if I want to integrate some alpha, and when you step alpha steps forward, then you forget about the rest. That's behind you. But in continuous case, well, you're pretty much doing the same thing. So you're stepping forward and going, okay, I'm over here, there's many steps, and these points are gone. And one of the interesting things here in this definition, and it's quite intricate, is that you see that in the standard definition of an integral in timescales or in discrete, we always go, if we write the integral, say a to t, we actually, when we write the sum, we go a to t minus 1. Now there's an accumulation point here, or point, that sits at the top here, which is actually t minus alpha. And any point less than this, as you go through, in terms of the kernel of this monomial, is 0. So all those steps before is 0. So they're gone. And that's sort of the defining factor of what's happening here. And I think that is the part where, well, at least Martin and I, when we wrote a paper together, we were fascinated by this. And this is something that, is really quite interesting. And even in the Goodrich book, they go through and go, yep, the kernel kills off all of these here. These monomials all gone before these points. But why? Why do you just write it like that? Why do you just say it is that? Because it doesn't really, it makes sense, but also when you're writing down a definition, there's something missing. Like in a general case, there is something there that you're just you're missing, because you start to put these points in, and you think, okay, well, yeah, it makes sense. It has to be this way. Because if I sum all the way up, and I put a minus 1 at the top of that, put a minus 1 up here, so t minus alpha minus 1, for instance, well, you're missing the last point. So if s is going up to, so let's say you've got s equals s equals a, let's say really simple, and then you've got t is a plus alpha. Well, that's automatically defined as 0 by the convention that we use, because that point doesn't exist because you're back 1 point, and that's defined as 0 in the conventions anyway. But it would be nice to know sort of why. And the sort of way that I've looked at it is, well, if you look up and you are thinking about you've already stepped alpha, you're actually moved already past that point. So anything in that gap is 0. So you're actually on another timescale, natural factor, which is this new domain that you have here. So you've moved up. So what I'm going to do in this framework, and this is sort of where it becomes more novel, is I'm going to define a forward shift projection. So I'm taking the order alpha.
Where's the real case?
The real case?
Yeah.
Well, you want to see the real case?
No, but in the real case, it's just t.
Yeah, it's just t.
Okay.
That's it. And that's fine.
Yeah.
Because remember, the graininess of what we have in the real case is 0. Right? And then where we're moving in those integrals is we're moving into decimal points anyway. So we're not really concerned about it at that point, because we're in the same time scale, still in the reals. We haven't moved into we haven't moved into a different domain on that new time scale after taking that integral. Right? So we're going to consider this as the shifted domain. So if you go through and have a look, and I don't know if I've got many there you can check, but you can easily check that in this case here, we're moving, say, with z plus alpha now. In the quantum case, you actually remain with the same topology that you're there, and you're still moving q, so you haven't changed how you actually move in terms of your shifts with sigma. So you still keep all those inherent properties of your original timescale. All right, so even H, again, still you're moving up alpha H. So you still haven't really moved that much. You haven't changed any of the inherent properties of your timescale. But what we've induced here is a shift in the domain. Okay, so we're moving up into this new timescale, T alpha. This is just this defined forward shift, and we define the projection back to that timescale as a one-to-one operator that's injected. So here we're going to call big pi alpha is the inverse of this particular forward shift.
I didn't understand the answer to the question of Martin, because you mean you are trying to do unification, but we don't get the...
No, we get, because in the real case there is no shift anyway. The T alpha is T.
Yeah.
Remember, the problem in the discrete is always this shifted domain. Yeah, I didn't understand at the beginning, but now I understand.
Yeah.
So wait 2 seconds.
Yeah, so in the real case, there is no shift in the domain. You always stay where you are, right? But in the delta case, you will always move, right, to the order. So this is a bit of this is not exactly right, okay? But I'm going to define this convolution. And I've called it, probably called it a fractional summation, yeah, but it's not really a fractional summation as of yet. It's a little bit different. So we'll define the convolution, and taking the kernel, which we'll call soon, which is K alpha, of the fraction of a convolution of alpha, which is shifted, of f in this domain here, theta, which is our shifted domain, or shifted domain, and we come back to this definition of just a regular convolution. Now you can reform this into the exact form which exists in Goodrich and Peterson for a convolution, and a few other Archigi as well, and Paul's book. So you can actually get everything back here in the same form.
And the real also mentioned.
And the real, yeah. Okay. Now the only thing in this case which is not the only thing that's technically not right, but I butchered, is really this is just theta in this case here, for a convolution. But for the fractional actual definition, it's a shift. So the convolution itself, this kernel kills it off, but this shift little thing here we'll get to it, to the actual definition, actually gives you the full result. But again, if you want to go back and look at the classical results, it's really just theta. Now, we can go one step further, we can pull this back, and what we see here is when we pull this back by the shift, we have this shift in the domain, and we end up here, a to t of our standard sort of convolution, and we end up in this term here, theta, with the shifted component. Now, we could go one step further here, and instead of having two, so instead of looking at this and saying, okay, in this point here, I'm going to shift the domain here, where S is still in the original timescale, and F is on the original timescale, we could go one step further and really probably properly define this a bit better for right-dense F functions. So we could actually have a more general convolution formula here, where we could sit purely on this T alpha space by taking inside of our radix function the projection of this shift as well. So what we've done in this case here is really replace the domain of f and projected that up. And then we can pull all that back, and as long as our shift is actually increasing, or decreasing, could be as well, increasing at least in the delta case, we have the following change of variables definition.
So pi alpha, what is pi alpha? Projection or something?
Projection, yeah. So it's the projection of the timescale. So this.
I guess now everything else
This is in
looks
T
good,
of
but
alpha,
then
and this comes down back to T alpha, T8. So that pulls whatever is, because this is in T alpha, So then we pull this back down to T.
In the discrete case, that means something minus alpha instead of plus, or?
Yep. In the discrete case, it's just minus, it's plus and minus. But if we want to look at it in a more general case, and we've got more arbitrary timescales, then yeah.
Then we have to first calculate that pi alpha on that time scale. That is not the major problem. The other one looks like not
Yes.
good. Yeah.
So when we're moving, I mean, that's not impossible.
Yeah, no.
So it's not, as we already have this guy.
Yeah.
You're just finding the inverse.
Yeah.
And then we can pull that all back though, and then we get rid of it anyway, because now we're back in terms of just the domain of t, or the original timescale that we're in. So now we're just in the original timescale, and we have this formula here, this convolution formula, which is containing all the shifts that we have, pulling back and back onto our original timescale. And we can see once again that we have this. We're going to be in a shifted domain where we are. So coming all the way back. So the goal here is sort of, okay, well, now with these new kernels that we might have here, how do we define an actual fractional sum? Okay, because I've only talked about convolution so far. I haven't talked about what is actually a fractional sum definition. I've just said here is the convolution, and this is what we're going to start with. We still need to come back and look at our Laplacian. Okay, so we will need our convolution theorem, where we have our Laplacian of 2, and that we can then yield what will actually happen. So the Laplacian of convolution is the Laplacian of, say, f and g. So convolution of f and g, the Laplacian of that is the Laplacian of f times the Laplacian of g. So we need to come back and look at that. So does that work in this case? And we will see shortly that it actually does. And everything gets sort of sucked in, and as the domains change, and I won't go through the proofs of this, but using Fabini, you see the shifts, and we actually come back and we get a semi-group property on this kernel K. So let's define a few Laplacians while we're here. So our standard Laplacian definition here is this one from timescales. As you can see, now if I change the domain, which occurs in, I'm not really changing the domain, I'm just changing the domain, but I'm just changing where I started here, then all we're changing here is this shift, okay? And this is done in many books, and in the discrete case, you can find these results in Goodrich and Peterson, and you can see what the shift looks like. And this is a really nice formula because you can actually take this and then you can shift back, and you can actually have the alternative definitions, how you combine a nabla and a delta as well. For our case, we need a bit more general. Okay, we need to generalize this a little bit further, and we need to go and think about our convolutions that I defined earlier for our shifts. In this case, for those two, then we're shifting in this, shifting at this point here in the space, and we're still maintaining this definition, but when we pull back, we're going to see we get a lot more little components coming out, a lot more shifts. So what we're really looking at here is got this Laplacian, I'm just shifting it across in the domains of this regional function here.
What is sigma alpha delta? It's the delta derivative of sigma alpha. There's a mu inside. No, under it. In the next line. Yeah, here, sigma alpha delta.
Yeah.
Yes, before the delta t.
Before, to the right.
To your right.
Go to the right. Stop.
Yeah.
Sigma alpha delta.
Yeah. So
But there's a mu in there. Sigma alpha is what? T plus alpha mu t, right?
Yep.
So this only works when mu is differential. No, I think you don't want to pull it back.
Don't want to pull it back?
Yeah, because then you need to assume that mu is differentiable, and we are getting back at the reals at the end.
That's true.
And also, the chain rule is not so clear how to go over here. Is that important, this putting back? Can we not just
We
leave
don't
it?
have to pull back, we can stay up there.
Yeah, the
That's
first
fine.
line is good.
It's just, yeah, just thought it'd be nice to be on one single timescale for a definition. Like, we don't have to pull back, we can still stay up there.
Yeah, because at that moment you restrict the time scale to u being differentiable.
Yes. So one of the still necessary conditions to define the fraction is still this, which is that the Laplacian of the kernel that we have inside that the kernel what we want to look at here is still s to the minus alpha. Now this is still the biggest problem. This is the problem because this is just assumed to be true in every case due to the interpolation of how close alpha is to n. And this is just done as a convention through fractional calculus.
Yes.
It's just assumed to be true. I would love to actually prove this. This would be very beautiful to prove. But just going back and thinking, okay, well this is what it has to be. That's what we will accept in this case. So we end up with a Mittag-Leffler function that can be generated here from this as well, which comes back to our standard results if we're thinking about Laplacian. And a few key little fractional calculus theorems and facts, results, as such is that the Laplacian of the exponential function here, alpha is 1 over s minus alpha, which is this is the classical result. Well, we're not that classical, but it's still a fundamental result, provided that as the limit we go, it ends up being 0. Okay, this if we take the Laplacian of delta, again, and I take it on the shift, then we end up with the exponential function of shift that's occurring. And again, of the step unit function here, where unit function, step function, we end up with the same, and we step here and we have s coming out the bottom. The reason why this is important is because we define this all for alpha really being between 0 and 1, and as we move up we go 1 plus 1 plus 1, and we step. So as our power goes up, we're multiplied by 1 on s. So the polynomial that we will define, that is induced from the Laplacian here, needs to satisfy this definition. So whatever polynomial is being pulled or coming out of our exponential in terms of Laplacian is defined by s on minus alpha plus 1. This, once we put alpha minus 1 in there, this yields back to our original definitions, and then thus we get our Mittag-Leffler functions on timescales. Okay?
Yeah, I agree with this, but is this definition, is it unique?
It's
Is the well defined like that?
it's well defined.
Yeah, if that's unique, then this is right. Yeah, that's the definition.
We'll find out. This might be the old one. Anyway, we'll find out. So yeah, we can get back we've got our classical Mittag-Leffler form here, where if we want to be, say, form, and then in the polynomials here, the polynomials in timescales, we come back to, if we want to generalize this as n alpha as we move forward. Now, the question though that I haven't answered is, which exists in the continuous case, and in fact discrete, is that there is a more generalized Mittag-Leffler function with further parameters that exist. I haven't looked at those. I've just kept it simple. We do end up getting the semi-group property holding for these fractional convolutions that we're showing, well, shifted convolutions that I was showing before. Therefore, this produces this result. And I've noticed this is actually the wrong one, but actually we actually get it shifts forward, and then it's actually the shift to beta, and then you get back into the full spectrum. Because when we're looking at this, when we're shifting, it's alpha plus beta. So, I realise this is probably the old slide, but it's unfortunate, but it's fine. So just coming back, or sorry, not coming back, moving forward. So defining how this actually looks, we have a convolution here, our original convolution with these two functions, and we can now define our fractional summation, delta fractional summation on the shifted convolutions. Now, again, this sigma is quite important. As I said, it actually pops up. You could just pull this to T. That's fine as well, because, as I said, if you look at the kernel, then things just get destroyed as you go backwards. Now, in this case here, these are just the polynomials, okay? Because it's defined by the Laplacian inverse. So this is the governing factor. I have written this one down here. As Martin said, if mu is differentiable, then we're a bit of a problem. So it works for most time scales, but not all of them in that case. So what we hope here, what we want, is that we have a function y satisfying this particular property here.
No sigma on the right? E minus sigma t?
Yeah, it should be.
No, I don't know. Because the left, how many, is it up to t or up to t minus 1 on the left?
It's up to, in this case we have 2 minus alpha.
So sigma t.
Yeah, there should be a sigma.
Yeah, there's some, yeah, so we have to look more at this one, yeah.
It does. Okay. Just give me 1 minute. Let me just, no, because I put these are the old slides. I just didn't, I think this must be it. That would explain a lot. Is this one?
Yeah. You are right, there is a sigma in there. So, and this is just if we return to this view. So I wanted to come back to the resolvent structure as well. So these are, again, this is the Mittag-Leffler function now, which is defined on that particular, for that particular problem 4, should have sigma alpha t in it. Right, that solves that previous equation.
very special case of when alpha equals 1, we get our classical result of 1 on Z alpha. Right? There's this, I've got this here, I just wanted to sort of go through and prove the different cases so we can see the unification of a definition of what it actually looks like in R, Z, and HZ that aligns with all the definitions in Peterson and all the other definitions that we have as one of those forms. So in the real case here, we can see that mu is 0, sigma is t, and our shift is just t, and we output the mononomial, which is then the kernel here for this particular case, for this particular mononomial, this is t minus s, alpha minus 1, which is our classical Riemann-Liouville kernel for our fractional druid. In HZ, we have our sigma is t plus h, mu is h, sigma alpha is then t plus alpha h. And as we shift through, and if you want to just think about h as 1 if you want, you can. So fine, it would be back to the integers. Then when we put it into our formula, this becomes our definition that we want to look at here for the h case. Now, h is 1, remember that shift with mu of t plus h. Right? So when we come back down, we actually end up in this particular case, which is, as you can see, if we start writing this out, with the shifted domain here now, what we have is s equals a of t. Remember, we shifted domain, so we're back here, and t exists in the original, and then you shifted domain. So t is the old h alpha minus 1, which is the mononomial, again shifted, and then s plus h. So this, if you pull this all back, and you change this here in the classical notation, which is just t, so if I put in there, say n, so if I go n equals t plus alpha h, for instance, and I change this through here, you end up with the shifted fractional sum that you get. And this is the exact same as what Goodrich and Peterson have in their books. Okay? And then we've got the continuous case. You can go further. And I've just got a little bit of summary here. We've got the real Z. It's a hybrid here. When we're starting to think about more complex timescales, we have to really start to look at the geometry and what's happening again. And I haven't gone through and proven all this, but I have proven the quantum case, and the quantum case works as well. Okay, so you get the definition coming out. So just a summary here. This is sort of where we ended up with, and in terms of a shift in alpha in that domain. Now, what I can say here is the only thing that we've really shown here is how do we unify in terms of the domain shifts of a fractional kernel. The one missing piece still is to answer this question, which is this. This is still the unanswered question. How does this actually come about? How can we have a proper proof that actually proves this, so then we can actually have a closed form for every single timescale? But in general, this is a general sort of unified approach that will allow us to move forward. So this is the next step in the frontier of research.
But sorry, you don't need to prove this box. You define them like that.
Yeah, but I still would like to. If I can find it, because alpha is the depth of how you go, and when we shift across, yeah, we're understanding how the domain shift, we understand the geometry of what's occurring in the timescale. It's a fractional operator in terms of the kernel, but we don't understand the depth of the position of we move, because that's defined by this. What if this is wrong, Martin?
No, the box is not wrong. You see that box?
I know.
You defined it there.
I know I defined it, but I would love to prove it from first principles that the inverse of z minus alpha equals these mononomials. I mean, it would be.
Right now, this monomial is defined like that. I mean, then you need to define it in a different way and prove this. If you already defined it in this way, this is proof. It's finished.
Okay, well, if you're happy with that. But yeah, I think there's still more there to be done. You know, that's,
The more is checking whether it's well defined. You know?
yeah. So we define it like this, but yeah, is it well defined? And that is the end of my talk. Thank you for putting up with me.
Professor, do you have any questions or remarks? Okay.
Could you show the previous slide, please? This induced time scale, the alpha. So the grayness this is the shift, right?
Yeah.
So the grayness is alpha mu.
What's that?
The induced grayness
Yes.
is the alpha times mu.
Yes.
So the points which are dense remain dense, and the points which are scattered
Yep.
get scattered with an only. So it's just like zoom in, zoom out. Do I understand well?
Yeah.
Alpha is smaller than 1, so it's zoom in.
Yeah, zoom in, yeah.
No, alpha can be also bigger than 1.
It can be bigger.
No, that was assumption that is.
No, it can be bigger. It can be bigger,
okay.
but it's easier when we start defining the fractional, like the actual definition. It's easier to stay between 0 and 1 because we can then just times by 1 on z, so we keep pushing forward each integer across. But yeah, so we just sort of zoom in, pull in.
So it is, to me, it's kind of nice because it does not create the new bad points like the left
Yeah.
and right hand
Yeah.
and that way around.
And that was sort of the motivation of doing it, with the geometry of it, and going, can we move in and then just sort of move out as such, just that we can keep the original timescale sort of properties that we've got.
And at the beginning, you showed some splitting of the integral over the right dense and right scattered points.
Yeah.
This integral is the Lebesgue or which kind of integral?
Yeah, I think we did on the bag. It's just the standard depth, the bag integral.
Also, it is not important for the rest.
Because it doesn't hold for Riemann, so that's why.
Yeah, so Tom? Yeah?
I just had a remark maybe. In the general case for the Laplace transform, it is a problem that we don't have the uniqueness. I mean, even in your computation somewhere, if you make the inverse Laplace transform, it might be a problem. Because we don't have the uniqueness of the Laplace transform one time scale. So there are just a few groups in the general case, but there is no general uniqueness.
Well, Svetlin tried to prove it. But yeah, it has been proved for discrete though.
The discrete is obvious.
But yeah,
If you have at least a few right dense points, it's a problem.
yeah, okay. I'll keep that in mind.
Tom?
Tom?
I saw a slide you had sigma of sigma sub alpha t, but sigma doesn't max on t alpha, but sigma alpha is t alpha to t alpha.
But see the commutative.
Okay.
So sigma alpha is still the same as sigma alpha sigma.
But the domain of sigma is t, but maybe I'm confused.
But the sigma is still the same on both timescales.
Oh, okay.
So
yeah, okay.
the shift still moves in commutative sense, back and forth. So you can swap them around. And that's what I found quite nice. It's a pretty simple proof if you're not convinced.
Just maybe I want to say something for those who know fractional and maybe not discrete fractional. So fractional is difficult, okay? But discrete fractional is much more difficult, and the main reason is the shift in domain. Oh, you get completely confused. I think it's this thing that at least that clears that problem. So, yeah, with the shift in domain, I mean, you know this very well, right? Not the other Peterson students, Goodrich.
Any more questions? So, thank you, Professor. Now we have lunch.
Was that your present, Martin? That's what you wanted? You said your birthday? When you got the cake?
Oh.
they know us.
We have this.
They didn't go up the ticket yesterday. They noticed it so much.
Is your non-uniqueness paper?
Yes, it is.
So how non-unique?
Take all our
You are told by the induced by the Oh, so this is the original grade.
That's the original.
I see. So I thought you were talking about induced grade. So this is the induced grade.
is on the TU alpha.
Yeah, this is the induced grade. Well, you have to define the induced greatness by sigma to alpha.
That is the original gradient.
This is the original one, but if you want to talk about the induced greatness or the induced type stuff, that would be mu sub alpha.
Yeah.
Is with this, no?
Or at least it is.
But you can write this out as 1 minus alpha.
Well, if you want to define this, it must be a times. So this would be sigma alpha of t minus t. It must be a times. With your formula, this is alpha times t. That's why I was talking about the zooming out. The gradient just induced gradient is a multiple of the original gradient by alpha.
Yes.
Yeah, that is true, yeah.
And then,
That was my point, to work with this one.
yeah, and then you that's right.
Okay,
You rewrite
So
that as-
then we also should have a different upper delta alpha.
Yes?
That didn't occur at all in here.
Yeah.
That could make some notation easier.
Yes.
That could avoid that sigma alpha delta thing.
Yes.
You already did all that, right? In that 5 minutes. Okay, so we go to the
I like it. I like it.
I'm sorry. I did this in 2 weeks. Well, thank
So you are not that smart. If you could do it in 2 weeks.
2 weeks.
No, this is very good.
Nah, it took me a month. But a long time to think about it.